Okay, we're starting with chapter 6. We're looking at thermochemistry, which is talking heat and energy. So we're just going to start with section 6.2, nature of energy. So real fast, chemistry is focused on the flow of energy. And the two forms of energy we're going to focus on are work and heat. Work is energy that's used to make an object move. And heat is energy used to cause the temperature to adhere to state increase. That means if it's gained, if it's lost, temperature would go down. Work is a topic we're going to talk a lot more about when you take physics. Don't sweat it too much now. Units of energy, the basic energy of unit of energy is the joule. We also get calories. There is a conversion between them, which you should be familiar with. Likewise, if you look at nutritional labels, you will see that there's something called a nutritional calorie. That is an uppercase C calorie, and that is equal to 1,000 normal calories, or this conversion here. Now, to talk heat, we need to talk system and surroundings. So, the system is the single thing we are studying. It can be as small or as large as we want. In chemistry, it's generally going to be either the chemical we're talking or the reactants and products involved in the reaction. The surroundings are everything else. So this leads us into section 6.3, the first law of thermodynamics, which simply states energy is conserved. And what this means is that energy is not destroyed, it is not created. If something like the system gains energy, it had to have come from somewhere. That means it comes from the surroundings. So if the system gains X joules of heat, the surroundings lost X joules of heat. There's no difference between that. Likewise, if the system loses energy, the energy has to go somewhere. It goes to the surroundings. But that statement itself is just qualitative. We're going to look at a quantitative way to do this as well. To do this, we're going to talk internal energy. The internal energy is just the sum of all the energy of a system. For example, let's say our system included hydrogen and oxygen gas molecules in a cylinder. The internal energy could include the kinetic energy of the motion of the hydrogen and oxygen molecules in space. It could involve the rotational energy, the vibrational energy as it's vibrating, and the nuclear energy in the nucleus, the energy of the electrons. There's lots and lots and lots and lots and lots of different types of internal energy, which we'll represent with a capital E. But the issue is we often don't know the complete E. As you can tell when we start talking like rotational and vibrational energy of molecules, it can get very complicated very quickly. But we are usually pretty good at finding the change in E, or delta E, or final minus initial. That's what delta means. A positive delta E means when the system, the thing we're looking at, because we're always looking at it from the view of the system. Positive delta E means that the system of the energy ends up more than it started. That means the system gained energy, which means the surroundings lost. Opposite occurs, negative delta E means that the system lost energy, meaning the surroundings gained. Now again, in chemistry, the change in internal energy can be caused by heat or work. Heat we represent with a Q, work with a W. Those can be positive or negative, as we see. By the way, internal energy is just the sum of heat and work. But again, the positive and negative there can be summarized by here. So again, saying that Q is positive means the system gains heat. Negative means the system loses heat. Positive work means work is being done on the system, and we're going to talk more about this later. This generally means the system's volume goes down. When the work is done by the system, that generally means that the system's volume goes up. This leads us directly into endothermic versus exothermic. In an endothermic process, the system absorbs heat, positive Q, exothermic, system loses heat, negative Q. As a note, your experience is not going to be the experience of the system. You are the surrounding. So you can imagine during any reaction, if you imagine putting your hand on it or near it, if your hand feels hot, you're the surroundings. That means the surroundings are gaining heat, meaning the heat came from the system, which means it would be exothermic. Likewise, if you put your hand near something and it feels cold, that means your hand is losing heat. That means the surroundings are losing heat. Which means if the surroundings are losing, it's going to the system, which means it's endothermic, plus Q. So now in 6.4, we're going to look at quantifying the heat and work. Again, most reactions that we see here in chemistry are occurring at a constant pressure. And again, remember that energy changes can result in changes in heat or work being done. Changes in heat are the easiest to spot because temperature will change as well. Work being done will, again, almost always be accompanied by change in volume, as I discussed. Temperature change and heat. So an amount of energy or heat is added or moved to a system, its temperature changes as well. More heat, higher temperature, lower heat, less heat, lower temperature. Very straightforward. The equation that we deal with this is this equation here. Heat is equal to capital C, called heat capacity of the object. The larger the heat capacity, the harder it is to change the heat or temperature drastically. So heat capacity is based object to object. A pool of water and a cup of water have different heat capacities, even though they're both water. The cup of water will be much easier to change the temperature of, so it would have a lower heat capacity. The pool of water, because it's harder to change its temperature drastically, would have a higher heat capacity. Now, to be more specific about this, we can talk specific heat or specific heat capacity. And what specific heat is now, instead of being based upon the object, it's being based on the substance. So a cup of water and a pool of water would have the same specific heat because it's now the amount of heat needed to raise 1 gram of a substance 1 degree Celsius, taking away the size difference. Now, there's also this thing called molar, not more, molar heat capacity, which is just like heat capacity or specific heat capacity. I'm full of typos. But for 1 mole of a substance. So this gives us a new equation, very important equation, just like Pivnerd is the equation for gas laws. This is the equation for heat. This is mcat, as I call it, the mcat equation. M is mass of what we're heating up or cooling down. C is the specific heat, and delta T is the change in temperature. Technically, that change in temperature should be in Kelvin, but because a 1 degree Celsius change is the same as 1 Kelvin temperature change, we can use Celsius as well. So we're going to look at a question: how much heat is needed to raise 300 grams of water from 22 degrees Celsius to near its boiling point 98? Then what is the molar heat capacity of that water? So again, we have this MCAT equation. I plug in the numbers. We were given the mass. We have the specific heat. We have the change in temperature. I plug it in. I get my answer. It's all good. It's all rosy. It's really that simple. For the molar heat capacity, we know the specific heat is 4.18 joules per Kelvin. We're going to turn the grams to moles. We do that through molar mass, and that's all that this is. So I start with the specific heat. This is me turning grams to moles using molar mass, so grams cancel, leaving with moles on bottom. I get my molar heat capacity. Now pressure volume work. So we're going to consider this reaction here. So we have this hydrochloric acid solution, we have zinc, we have a piston, and then we dump the zinc in, and it fizzes, raising this piston up. So the system is doing work. So we call that PV work, or pressure volume work. And when pressure can remain constant, as in this example, and to be honest, in most examples here in chemistry, then we can say work is equal to negative P delta V. The negative sign is there to ensure consistency amongst our sign. So again, the system doing work increases volume. So volume goes up, pressure has to be positive. That means work is negative. That means the system is doing work. So that, again, is just maintaining that consistency that we saw before. Okay, this is a very, very, very short section. So to find heat change, we do a process called calorimetry. To do calorimetry, we use a thing called a calorimeter. That's it. That's the section. So moving along to 6.6, enthalpy. This sounds way more complicated than it is. Enthalpy accounts for heat flow when there's no work but PV work being done, which is what we see in chemistry. That's what we see there. Enthalpy is symbolized with a capital H. And so we can say enthalpy is equal to energy plus PV. And again, PV being our work. So changes in enthalpy, if it's happening at a constant pressure, which, to be honest, anytime we're dealing with heat changes or enthalpy changes here in chemistry, it'll be at a constant pressure. Then this is what we get. And then through the magic of math, we can also then find that heat equals enthalpy change. And this is the secret. So enthalpy change and heat change at a constant pressure mean the same thing. So the takeaway, we can talk enthalpy, we can talk heat, for our purposes here at AP Chemistry, they mean the same thing, period. So again, why do we bother with this? It's technically to prepare you for higher levels of chemistry and physics, but heat at a constant pressure is easier to measure than internal energy, so that makes enthalpy more useful. But for most reactions, the difference between delta H and E are tiny because P delta V tends to be small, so it doesn't matter anyways. Now again, when delta H is positive, that means Q is positive. That means the system gained energy. That means it's endothermic. Likewise, if delta H is negative, the system lost energy. That means it's exothermic. We know this. So again, positive or negative real quick. So ice cube melting, if I feel that, it feels cold. To melt, things have to gain heat, so that makes it endothermic. Burning, releasing heat, it feels hot if you put your hand near it. Again, your experience is the surroundings, not the system. So because your hand is feeling warm, that means that your hand is taking in heat. If your hand is taking in heat as the surroundings, that means the system is losing heat, which means exothermic. So there you go. You can do stoichiometry with this. So we can talk enthalpy of a reaction. That's just the heat change associated with a reaction, or heat of reaction, or heat of reaction. All means the same thing. So for instance, the combustion of hydrogen, we have this equation, and then we throw this little term here at the end. That's telling us that for this reaction, it generates this much heat. Again, it's exothermic. It's generating because of the negative there. Same reaction as before, so delta H is given without stating the amount of chemicals involved because it's based on the moles. It's based on the stoichiometry. So what it's saying is for every 2 moles of hydrogen that burns, we produce 483.6 kilojoules of heat. Any balanced equation that I have that also shows the enthalpy change, we call a thermochemical equation, and we can do a modification of stoichiometry with. Now, to do this, we have to recognize a few guidelines first. 1, enthalpy is what we call an extensive property. This means that the magnitude of delta H is directly proportional to the amount of reactant. In other words, more reactant, more heat. We double the reactant, double the heat. Simple as that. If we reverse a reaction, we reverse the heat sign. So if the forward reaction as written is positive, endothermic, the reverse of that reaction would be negative, exothermic. And finally, state matters hugely. Chemicals in different states have differing amounts of energy, so you must pay attention. You must write down states of matter. Vitally important in this. So an example, we're going to see how much heat is released when 6.75 grams of methane gas is burned. So we have our reaction. At this point, it's a modification of stoichiometry. So like all stoichiometry, we start with what we were given. We were told 6.75 grams of methane. In stoichiometry, we start with what we're given. We turn it into moles. So I divide by the molar mass to cancel out grams of methane. I'm now in moles of methane. Now, normally we would then do a mole-to-mole ratio, but here's the trick. What we're going to do is we're going to do a mole to heat ratio, which is what we see right there. Now, this bottom is 1 mole of methane because methane has a coefficient of 1. If methane had a coefficient of 5, it would be 5 moles on the bottom. That negative 890 up top is the heat change that we see right there. So we get our answer, 375. But wait, Ms. Anderson, I hear you ask, what happened to the negative? Well, the problem said how much heat was released. That means it's implied that it's exothermic, so the negative is implied. Okay, so now that we've seen what calorimetry is, again, it's the experimental method that we use to find heat change. We're going to see how to do the calculations with calorimetry. It's the MCAT equation. Everything, this chapter, is either thermochemical equations or MCAT. So when we're doing MCAT, the MCAT equation, again, Q equals MC delta T. Q is heat. M is the mass, C is the specific heat, delta T is the temperature. Now the trick of this, the thing that we're finding the temperature change of is not the system. The way that calorimeters work, and I'm going to show a picture of this, I think on the next slide, is that you're finding the temperature change of the surroundings. The reaction is taking place in a solution. So the delta T is the delta T of the solution, usually of the water. The specific heat is the specific heat of the solution. The mass is the mass of the solution. The heat change is the heat change of the solution. The solution is the surroundings, not the system. And that becomes really important because it switches the sign that we're dealing with. So if the solution heats up, if the solution increased in temperature, gained heat, that means the system lost heat and it's an exothermic process. It's just a little step we have to remember. And so again, we assume that the heat gained by the solution equals that lost by the reaction, or vice versa. So this is what a coffee cup calorimeter, the most standard calorimeter that we're going to see, looks like. You have a coffee cup, maybe two if you're feeling fancy. You have your solution in there. You have the reaction taking place. You have a thermometer. This one is ooh la la fancy because it actually has a stirring rod in there. I never use a stirring rod. I just use the thermometer to stir. And I never use a wooden cover. I just use a piece of cardboard with a hole in it because I'm fancy that way. So here's an example problem. So magnesium reacts with hydrochloric acid. Here's the reaction. So we add in a certain mass of magnesium. We combine it with enough HCl to make 100 milliliters of solution. We say assume density of water. This is making the problem seem a lot more complex than it is. Water has a density of 1 gram per milliliter. So because it's 100 milliliters of solution, it's 100 grams. If we're assuming the specific heat of water, 4.18, temperature goes from 25.6 to 32.8. So now we just assemble our MCAT equation. Now, this piece here is a little controversial. And on the AP test, they actually allow this really two ways. But this is the habit I'd like you to get into. The mass is the total mass involved. So take the mass of like your water, and in this case I'm adding in, or in this case the hydrochloric acid solution, and the mass of the magnesium, that's why it's 100.158. Add in all the masses together, it's a safer bet. We have our specific heat, we have our two temperatures, we have our delta T, it's the temperature difference between the two. I plug my numbers in, I get my answer, that's it. Now again, notice here temperature went up. Temperature went up, that means the heat change of the solution is 3.01 kilojoules, which means the heat change for the reaction would be negative 3.01 kilojoules because, again, the reaction is opposite that of the calorimeter. So we're nearing doneness on here. Hess's law, if you followed along with me in order this year, you know that I do the textbook out of order. Hess's law will be very straightforward after we've talked about reaction mechanisms. So here's the deal. Many heats of reaction have already been measured and recorded. So what we can do is we can calculate the enthalpy change of a reaction based upon the pre-recorded values of other standardized reactions. So that means we don't have to perform calorimetry for everything. We can use these pre-made heats. Now, again, delta H, enthalpy, depends on the amount of matter undergoing the change. We talked about that earlier. The nature of the initial state. So again, the amount of chemicals matter, the states matter. This means it doesn't matter if the reaction takes place in one step or a series of steps. To put this into context with our reaction rates, it doesn't matter if it's a multi-step mechanism or an elementary step mechanism. It doesn't matter. What matters is where we start and where we end. That's what's really what the reactants are, what the products are. What happens in the middle doesn't matter. So, a few things. So if I have a reaction, if I double all the coefficients, I double the heat. If I tripled the coefficients, I triple the heat. If I reverse an equation, you reverse the heat. So we see reaction 1, I see reaction 2. The only difference between them is reaction 2 is the reverse of reaction 1. So whatever the enthalpy change of reaction 1 is, reaction 2 would be the same, but opposite sign. Finally, if I can take a chemical equation, if I can express it in steps, the delta H for the overall reaction is equal to the sum of the heats for each individual step. We call this Hess's law. For example, as a note, by the way, in Hess's law, you would be provided with the steps. You do not have to make them yourself. So let's say this is our overall reaction, and it's thought of as two steps. Step 1, step 2. So the first step, we're reacting methane with oxygen. We're forming carbon dioxide and water gas. Then the second reaction, we're turning the water gas into liquid water. Now, if I add these two equations together, I can see 2 moles of gaseous water, 2 moles of gaseous water. They add up to the target equation I see here. That means if I knew the delta H for the first reaction and the delta H for the second reaction, then the enthalpy change total would just be the sum of the individuals. So, again, let's say this reaction here, so this gaseous is negative 802 kilojoules. Second one is negative 88 kilojoules. Again, just if I add them up, I get what I want. So that means the official heat of reaction for that reaction would be negative 890, because negative 802 plus negative 88 equals negative 890. It's as simple as that. Now, sometimes we have to manipulate the two equations. So this is our target equation there. So if that's our target equation, we have to look at the individual equations and see how we can manipulate them to make what we want. The way I recommend this is look for something unique, something that each component adds uniquely to the total equation, and make sure it's on the right side of the equation, make sure it has the right coefficient. So looking at this, I see that nitrogen is unique with that first equation. Nitrogen initially has a coefficient of 1, and it's supposed to have a coefficient of 1. Nitrogen is originally a reactant. Nitrogen is a reactant in the target equation. So I'm going to leave the first equation as is. Now the second one, notice they both have oxygen. So oxygen's not unique. I'm not going to worry about oxygen. But I see this NO2 is unique. But looking at the second equation up top, right there, I see NO2 as a reactant, whereas I want NO2 as a product. Now the coefficient is right, but it's on the wrong side. So that means with this reaction here, the second reaction, I need to reverse it. And if I reverse it, the delta H goes from 112 to negative 112. So putting all this together now, so again, the target, nitrogen's on the left, so we're going to keep the first reaction as is. N2 plus O2 makes 2NO with a delta H of 180. The second reaction we're going to reverse, because again, this NO2, 2 moles of NO2 needs to be in the products. So I reverse the second, so I see 2NO plus O2 makes 2NO2. Now because I reverse the reaction, that also reverses the sign there. So it goes from 112 to negative 112. Now if I add these up, again, I didn't pay attention to the NOs. They end up canceling. So I would get N2 plus 2 O2s makes 2 NO2. So that's my target reaction. And then the delta H would be the sum of the two. So 180 minus negative, so minus 112 or plus negative 112 would be a 768. Assuming my math is right. I forgot to grab a calculator. I just grabbed a calculator. You're playing along at lightning speed as this is live. Hey, look, I did mental math right. So yeah, that's how that works. Let's look at another example. So now we're going to calculate delta H for the following. So this is our target reaction, and we're provided these three. So we're going to walk through this piece by piece by piece. So again, target equation is up top. So looking at this, first equation, it's not giving me too much. So I don't see anything in there that's really unique. I see some oxygens, nothing too striking. Second equation, I look at it and I see that the N2O5 is on the wrong side and has to be reversed. So I'm going to take that second equation, so we'll call it equations 1, 2, and 3. So that second equation is now going to be, I have to double and I need to reverse. So I'll call it negative 2x, double and reverse. So we would get 2, let me erase, 4 HNO3 goes to 2N2O5 plus 2 waters. Now in this case, the only water we have is liquid, so I'm not being too careful with the states of matter. Now looking at that third equation, what do we have there? I see the nitrogen being unique. Now again, in the third equation, I see half a mole of nitrogen. I need 2 moles of nitrogen, so I actually need to multiply it by 4. So equation 3, I want to still reactants and reactants, but I need 2 moles of nitrogen, so I'm going to multiply by 4. So that gives me 2 moles nitrogen. Now 3/2 times 4 is 6. Oh, I'm going to rewrite that. My apologies. I don't know why I wrote moles. The word moles. So again, we would get 2 nitrogens plus 6 oxygens. 3/2 times 4 is 6, I think. Plus 2 hydrogens makes 4 HNO3. Okay, so we're in pretty good shape. So looking at this is kind of eyeballing where we're at so far, because that first equation was still kind of weird. I can see that as is, the HNO3 cancels, which is good because we don't want that. And let's see, the N2O5 is in the right place. Water though, water is a little funky, and that's going to be our thing there, because looking at the second equation, it has this 2 water there, and I don't want there to be 2 waters. We need to cancel out waters. And the third equation doesn't have water at all. So to deal with the water, I'm going to take that first equation. I need to cancel out 2 waters, so which is a product already. So I'm going to do reverse it and times 2. And we'll kind of see how that plays out. So if I reverse it and times 2 from the first equation, I would get 2 waters yields 2 hydrogens plus an oxygen. Now when I look at this, I see some interesting things happening. I see water in the products, water in the reactants, 2 and 2, so they cancel, that's good. I see oxygens. 1 oxygen cancels 1 from there, which makes it a 5. That's good. And I see hydrogen as a reactant, hydrogen as a product, 2 moles of each, that cancels. So looking at what's left over, I see 2N2 plus 5O2 from right there. Oh, that was really far off. 5O2 goes to make 2N2O5. So that's right, that's what I want. So now to find the heat change, I have to add up all the heat. So I take that first one, I would double it, switch the sign. The second one, I would double it, switch the sign. The third one, I would do 4 times the amount, keep the sign. So, just to not leave you suspenseful, negative 285.8 times 2. So that first one gives me now 571.6. Again, it's going to be a positive because I reversed it. The second one, 76.6 times 2, 153.2. Again, doubled and reversed. And the third one times 4. So negative 174.1 times 4. So negative 696.4. So now we add all these up. So negative 696.4 plus 571.6 plus 153.2 gives me a whopping 28.4 kilojoules. So again, if you just pay attention to what's unique in each equation and what coefficients does it have to be, and where does it have to be in the equation, reactants or products? That'll guide you through it. This was a tough one. This was a tough one. Okay, and this is our last section of the chapter. Yay! So, called enthalpies of formation. So basically, we saw using calorimetry or Hess's law, we can calculate the enthalpy change for lots of different reactions. Now, most experimental data is given by the type of process. So for instance, enthalpies of vaporization is all about the heat change to boil something. Enthalpy of fusion would be the heat change to melt something. Enthalpies of combustion, the heat change when things are burned. Enthalpy of formation, this is going to be the big one. This is going to be the heat change when making a compound from its elements. So we also call it a heat of formation, and that's what this chapter or section is about. And we often see this little symbol here, delta H, again being enthalpy change, the sub F meaning formation. And we talked about that already. So, enthalpy change depends upon conditions of temperature, pressure, and state. So to be able to compare enthalpies of different reactions, we're defining a set of conditions called the standard state conditions at which these enthalpies are tabulated. We call standard state 1 atmosphere pressure, 298 Kelvin, which is 25 degrees Celsius. One thing I want to make clear, when you learned in gas laws about STP, the standard temperature there was 0 degrees Celsius. So STP temperature is 0 Celsius. When we talk standard state in thermochemistry, it's 25 degrees Celsius. Yes, I know it's confusing. No, there's nothing we can do about it. So the standard enthalpy change of a reaction is defined as the enthalpy change when all reactants and products are in their standard state. So think about the state of matter that those things would be in at 25 degrees Celsius. And if that's the case, we throw in this little not sign there to indicate standard conditions. So we can then talk standard heat of formation. So that's the change in enthalpy that forms when 1 mole of a compound is formed from its elements, with everything being in their standard states. Now, if an element exists in more than one form under standard conditions, the most stable form is what we use for the formation reaction. So for instance, when we talk oxygen, we use O2, not O or O3, because O2 is the most stable form of oxygen. Carbon is graphite and not diamond, and values are given in Appendix 2, just pages prior to what you were already dealing with in terms of Kas, Kbs, Ksps. It's the pages before that. Now, the stoichiometry of a formation reaction always indicates that 1 mole of the desired substance is produced. That's what it's for. The heat of formation is the heat change to make 1 mole of that substance. So we'll often see the delta, standard heat of formation in kilojoules per mole. Now, by definition, the standard enthalpy of formation of an element is 0. Well, that's because, again, heat of formation is the heat or the energy change needed to make that thing from its elements. If it's already that element, then it's no energy to make it the exact same thing. That's said there. So we're going to play a little game. We're going to identify the standard enthalpy of formation equation. So that first one, would that first one be standard enthalpy of formation for the equation? So I see we're making 1 mole of the product. I see elements in their standard state. So yeah, absolutely. How about that second one? No, 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 because that is a 2 there. We cannot have a 2, and it has potassium as a liquid. Liquid potassium is not standard state. Should it really be solid, not liquid? Bad me. Finally, the second one. Oh God, no, no. Again, it's the heat to make 1 mole. This is the reverse, actually, of standard state. And diamond is not the most stable form of carbon. It's graphite. So lots of problems there. Now, we can use enthalpies of formation to calculate the enthalpies of reaction. So basically, it's in the background, it's Hess's law. So we can actually look up the heats of formation of every substance in a formula. And we can use those to find the heat of formation of a reaction. So for instance, this reaction here. If we look up the heat of formation of C3H8, oxygen, carbon dioxide, liquid water, we can actually find the heat of formation of that reaction. So again, that's what we have. So what we would do, and again, technically what's here is there's the 3 that we're going with. So again, I'm going to do some hand waving. Don't worry about this too much. The C3H8 is a reactant, so I've actually reversed the sign. So I have 1 mole of the C3H8. I'm switching the sign on it. The carbon dioxide, we want 3 moles of carbon dioxide in the products. So I take the heat of formation of carbon dioxide, multiply it by 3. Liquid water, I need 4 moles. So heat of water, 4. Notice I left off the oxygen. Why did I leave out the oxygen? Well, that's because oxygen's an element. It has a heat of formation of 0. So we can add them all up. There is an easier way to do this. So again, I can add these all up. I look them up. I look up the values, blah, 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 blah. I get my value. Again, nothing special there. We look up the values. We make it work. There is an easier way. The easier way is sum of the products minus sum of the reactants. It's that simple. Look up the reactants. Look up the products. Add up all the heats of formation of the reactants all together. We do have to multiply each by their coefficient. Add up all the heats of formation of the products, again, paying attention to coefficients. So if something has a coefficient of 2, we multiply its heat of formation by 2. If something has a coefficient of 7, I multiply its heat of formation by 7. Then I do products minus reactants. We're going to see that a lot. A lot. Products minus reactants. So we're going to do an example. So here we're going to do combustion of ethanol. We have our reaction. So I have my reaction. So what I do is I look up my products. I see carbon dioxide. I see water. I see the ethanol. I see ethanol. Now, O2 is not given in the book. Why isn't oxygen given in the book? Well, it's because oxygen is an element in its standard state. So it actually has a value of 0. So what we do now, very straightforward, products minus reactants. So I look at my products. So heat of reaction. So I look at my products. I see 2 moles of carbon dioxide. So 2 times negative 413.8 plus 3 times the water, negative 285.8, products minus reactants, negative 277.6. And then you run it through your calculator and you get the answer. I'm not overly concerned with what the answer is. You would just get that. My recommendation when doing this work, show your work, solve this first, then do the subtraction of products minus reactants as a second step. Don't do it all in one step. It's easier to make a mistake that way.